Automotive and industrial systems operate in demanding environments, require higher performance and reliability from onboard systems that are increasingly becoming electric-based, such as steering, braking, suspension, cooling, and general relay control. The performance of onboard systems is increasing as voltage ranges continue to rise. Peak currents rise to hundreds of amps, and at times to enable these systems, they need to be as fast as possible. Increasing reliability is driving manufacturers to have less mechanical systems and more solid-state systems that include protections for the power source, the loads, and the solid-state power devices. Hi, my name is Mark Mullen. I'm a design engineer in the Power Products Group at Linear Technology, now a part of Analog Devices. I'm going to show you how to use the LTC7000 protected high-side driver to resolve electrical design issues in automotive and industrial applications. The LTC7000 is a fast, high-side N-channel MOSFET gate driver that receives a low-voltage digital input signal and can fully turn on or turn off a high-side N-channel MOSFET whose drain can be 135 volts above ground with 35 nanoseconds of propagation delay. The LTC7000 includes protection features such as overcurrent trip, fault flag, undervoltage lockout, and overvoltage lockout. There are many applications in the industrial and automotive market that will find this useful, such as static switch drivers, load supply switch drivers, and relay replacements. Looking at the basic function, the LTC7000 receives a ground referenced low voltage digital signal on the INP pin. Level shifts this signal up to the VN voltage and controls on-chip, low impedance, pull-up and pull-down devices, which can quickly turn on or turn off a high-side N-channel MOSFET whose drain can be 135 volts above ground. The propagation delay from the low-voltage INP signal to the N-channel MOSFET being fully enhanced or fully turned off is around 35 nanoseconds, which enables many applications. The powerful output devices keep the external MOSFET in the state commanded by the low-voltage INP signal, even if high-voltage and high-frequency transients couple from the power MOSFET back to the driving circuitry. The LTC7000 powers the output devices from a floating supply connected between the boost and TS pins. This floating supply is powered from an internal charge pump, which allows the external MOSFET to stay on indefinitely. The floating supply between the boost and TS pins is internally regulated to 12 volts, reducing power losses associated with the on-chip resistance of the external MOSFET. The LTC7000 protects the external N-channel MOSFET from overcurrent damage by sensing the voltage across a sense resistor placed in the drain of the MOSFET and turning off the MOSFET if the voltage across the sense resistor exceeds 30 millivolts. The low current sense threshold voltage of 30 millivolts reduces the power loss associated with sensing the drain current of the MOSFET. For example, if the application current trip requirement is 10 amps, then only 300 milliwatts maximum will be dissipated in the sense resistor. For additional flexibility, the current sense threshold voltage can be optionally adjusted between 20 millivolts and 75 millivolts by varying the voltage on the I-set pin. The voltage on I-set is divided by 20 to set the current sense threshold. A 10 microamp current flows out of the I-set pin, so just placing a resistor from I-set to ground will adjust the current sense threshold. If I-set is floated, the current sense threshold defaults to 30 millivolts. If I-set is grounded, the current sense threshold is 20 millivolts. This flexibility affords quick board level adjustments in the current trip threshold for applications. A timer pin is included so that an overcurrent condition will not immediately turn off the external MOSFET. Connecting a capacitor from timer to ground sets the internal delay period before the external MOSFET is turned off during an overcurrent fault condition. The turn-off delay period can be set from a minimum of 1.4 microseconds if timer pin is open to tens or hundreds of milliseconds if capacitors in the microfarad range are used on the timer pin. The same capacitor placed on timer also sets a cool-down period before the internal circuitry will automatically try to turn back on the external MOSFET. The retry duty cycle is around 0.06%. The overcurrent trip point and timer capacitor should be chosen so that the external MOSFET is protected by keeping the MOSFET within the safe operating area as specified in the MOSFET datasheet. Once an overcurrent fault condition is detected, an open drain fault pin is pulled low. The fault pin remains low until the fault condition is removed and the external MOSFET turns back on. The LTC7000 can easily be configured to latch off instead of automatically retrying by adding a 100k ohm resistor in parallel with a timer capacitor. The turn-off delay for an overcurrent fault will still be set by the timer capacitor, but the LTC7000 will not automatically try to turn back on the external MOSFET after an overcurrent fault. The external MOSFET will not try to turn back on until the low voltage INP signal is cycled low, then back high. In this configuration, the open drain fault pin will be pulled low once an overcurrent fault is detected and will remain low until the INP signal is cycled low, then back high. The average current flowing through the high side sense resistor can be monitored by measuring the voltage on the IMON pin. When the external MOSFET is on, the voltage that appears on the IMON pin is the sense voltage, Vsense plus minus Vsense minus multiplied by 20. For example, if the sense resistor is 2 milliohms, then an IMON voltage of 400 millivolts indicates there is 10 amps flowing through the sense resistor. The averaging time of the IMON voltage is roughly 100k ohm multiplied by any capacitance on the IMON pin. For example, if the capacitance on the IMON pin is 10 nanofarads, then the averaging time of the IMON voltage is around 1 millisecond. The LTC7000 can protect loads from overvoltage and undervoltage conditions on VN. A simple resistor divider from VN to ground with taps connected to the run and OVLO pins will set a valid operating voltage window for the load. When VN is outside the operating window set by the run and OVLO pins, the external MOSFET is turned off and the load is protected from potential damage or malfunction. Another undervoltage lockout is also available for the VCC supply by using the VCC UV pin. The VCC undervoltage lockout can be adjusted between 3.5 and 10.5 volts by varying the voltage on the VCC UV pin. A 10 microamp current flows out of the VCC UV pin, so just placing a resistor from VCC UV to ground will adjust the VCC undervoltage lockout threshold. If VCC UV is floated, the VCC undervoltage lockout defaults to 7 volts. If VCC UV is grounded, the VCC undervoltage lockout voltage is set to 3.5 volts. When the voltage on VCC is below the undervoltage lockout set by the VCC UV pin, the external MOSFET is turned off. In conclusion, the LTC7000 is a flexible, rugged device that allows automotive and industrial manufacturers to increase the performance and reliability of their systems. The voltage range of up to 135 volts, built-in protection features, strong drivers, and fast turn-on and turn-off times allow manufacturers to continue to develop systems that add value and reliability for their customers. For more information, please visit our website at linear.com. Thanks for watching.